Okay. Santhosh, shall we go for live?
Yeah, 2 minutes.
Yeah, 2 minutes.
I started the live, sir.
Started the live, sir.
Okay. You have started. Santhosh, you have started?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Yes. Okay. Okay. Good evening, everybody. Good evening, participants. So let us wait for a few more minutes. We can wait for 1 minute. Later we can start.
Started the live, sir.
Started the live, sir.
You have started. Okay. Okay. We can start. Good evening, all. I welcome all for international webinar on turbocharged IC engines and market expectations. Now I request Dr. K. Balasubramaniam, Head of Department Mechanical Engineering, MEENAKSHI Engineering College, to inaugurate the program and welcome our chief guest. Dr. K. Balasubramaniam, Head of Department Mechanical Engineering.
Everybody who was present today for this international webinar on turbocharged IC engines. Our guest, chief guest is,
Today's our executor today is alumni of St. Joseph's College of Engineering in Chennai, in UK. Today, I'm working as a technical project leader at and Cummins Turbo Technologies in Huddersfield, UK. Also in UK in Scotland. So I know a little bit about your configuration. So a person who is going from India to UK for higher studies and getting himself personalized and then to this particular easy job. And that too in Cummins, which people are knowing about the Cummins, which is a pioneer in 47. Because also Cummins and he is acquired a lot of higher ups to reach this particular present position. So instead of any time, I want just knowing about it.
When you add more air into the cylinder. So in theory, if you compare the value on the left side to the value on the right side, you could double the power. You basically need to compress the air and then put it into the intake manifold. So in the previous slide, you saw about pressure charging. So you have to put pressurized air into the intake manifold. And the way you do it is by using a compressor, and then the compressor will be connected to a belt to the crankshaft, and then it will be driven by the crankshaft. So by doing that, the compressor will be putting compressed air or pressurized air into the intake manifold. So by doing it, we'll have pressurized air into the engine. The other way to do it is by using the exhaust gear. So you know that in the 4-stroke engine, the last stroke is the exhaust stroke. And in the exhaust stroke, you will probably have the exhaust gases coming from the turbine outlet, or we'll get the exhaust gases coming from the exhaust manifold, which will pass through a turbine stage. And And what that does is, and this is a turbocharger where you'll have a turbine stage and a compressor stage. The turbine stage will basically spin because you're putting in air from the exhaust manifold. And because it's connected to a shaft between the turbine stage and the compressor stage will also sort of rotate because the turbine stage is moving and there is a shaft which is connected, and that will start compressing the air, and then that compressed air will be fed back into the engine. So these are the two different ways of how you can put pressurized air into an IC engine. The first way is by a mechanical way, by connecting a belt drive through gears, through mechanism, and then that basically gives you the compressed air into the engine. The second way is by using the exhaust gases itself, which are coming from the engine, which will sort of move a turbine, like a turbine wheel, and then that will be connected to a compressor stage where there'll be a wheel again, which sort of moves around, and that will sort of start compressing the air and feed that compressed air into the IC engine. So these are the two ways of providing pressurized air into the IC engine. So I've just shown you a picture of a Cummins fixed geometry turbocharger. So the turbine side is this side over here where my mouse is pointing towards. So this will be connected to the exhaust manifold over here. And because the hot gases are passing through here, this wheels rotate. And because there is a shaft connecting to this wheel, this is the compressor stage. So this will start rotating as well, and it will sort of compress the air and provide it back into the engine manifold. Okay. So these are the two ways of how you can how you can provide pressurized air into the engine. So the next topic I want to share with you is about the supercharged engine. In terms of the before I go, there are some people, Mr. Vadivel, there are some people in the waiting room. You want to add them, or should I leave them all?
You can admit them, sir. Admit those participants.
Okay.
I don't want to disturb you, so only I didn't tell you anything.
No, it's okay, no one. Right.
You can give the admit all.
Yeah. So in a supercharger, so going back to the previous example, so what happens is you basically have pressurized air, which we feed from the supercharger. And once you have the fuel, obviously it'll combust, and it'll basically have the exhaust gases coming through the exhaust port. Now we talked about the naturally aspirated engine, which basically have 150 kilowatts of power. And what happens is that with a supercharged engine, we basically create more power because we are saying we are giving in more compressed air into the engine, which means there is more power. But because it's a mechanical device and it's connected through to the engine crankshaft, it'll have some losses because of that, the way it's been connected to the crankshaft, the losses from the connection. So which means that we have to take away that 50 kilowatts, which is required to move the mechanism in order for the compressor to compress the air, which means the resultant output will be around 200 kilowatts. So this 200 kilowatts obviously is high. It's higher than the naturally aspirated engine. However, it's not getting the full power output because it has to sort of take away the losses from the mechanism itself. But in a turbocharged engine, what you will sort of find is you will have the exhaust gases passing through the exhaust port from the engine, which sort of is fed back to the turbocharger, which is then sort of compressing the air. And then the compressed air will basically be fed back into the intake manifold. So it's like a cycle. So you feed the exhaust gases, gets compressed air gets fed back into the engine, which means the power output is the highest that you can get. There is between the naturally aspirated, the supercharged, and the turbocharged engine. The turbocharged obviously has the highest power output. Okay, so that's pretty much the examples that are sort of compared between a naturally aspirated engine, a supercharged engine, and then a turbocharged engine. So the next one that we are gonna see is so we've been talking about different engine configurations. So we talked about naturally aspirated engine. We've talked about pressure charging. Why is pressure charging required? And I've shown you the advantages of that. And also after showing why we need pressure charging, I've also showed you the different ways we can do pressure charging. So one of them is supercharging, another one is turbocharging. So, and you can clearly see the difference between the three configurations. So, and now I'm going to explain about why do you need to turbocharge IC engines. So the first one is more power output. When I say more power output, I have already shown you the examples in terms of how a naturally aspirated engine sort of gives you takes over the atmospheric air, gives you a certain output. If you pack in more air, you by supercharging method, you obviously get more power output, but you need to take away the losses. But in terms of turbocharger, you basically have the full output that you can get from the engines because you're packing in more air. If you pack in more air, there'll be obviously more combustion, and then the density goes up, and thereby the power goes up as well. So that's why you have a more power output with a turbocharged engine. Emission legislation. So we all know that with an IC engine, there'll obviously be emissions. So when I say emissions, think about it as if you have a naturally aspirated engine, what you have is smoke. You'll have emissions of smoke, carbon dioxide, nitrous, and NOx, particulate matters. You have quite a few of emissions, which sort of as a byproduct of IC engines. With turbochargers, because you're packing in more air, what that means is that you're allowing for a much more better combustion process. So if you have a combustion process which is not that good in terms of an air fuel mixture, the resultant will be sort of smoke, which you don't want because the whole world is aiming for a smoke reduction and then emissions reduction, and that is the main reasons why a lot of countries are focusing on much more greener technologies. A turbocharger helps to reduce emissions because it helps to sort of aim for that better more air fuel combination, which means you end up in a much more efficient combustion process, which means obviously it results in your emissions reduction. And also having a turbocharger will also help downstream basically, which means that after a turbocharger, there are certain elements on an IC engine. If you see, there are technologies such as EJR and other latest technologies, DPF, all the sort of emissions oriented or after treatment systems, that what they call as. The turbocharger helps all those systems because it also gives you that back pressure. So in terms of back pressure, I mean it as a sort of a pressure which is coming from your turbine side, which sort of helps you raise the temperatures for EGR and all the after system, so that it basically helps you to achieve the right temperatures to tackle the emissions. So that's one of the key reasons why we need a turbocharger on an IC engine. The next one is about engine downsizing. So obviously, if you think about it as if you're using a naturally aspirated engine, if you need a certain power output, you obviously need to go with bigger sized pistons, bigger sized engine, cylinders to give you that particular power output. Because I showed you on the first slide how naturally aspirated engine works. But if you need to get the same power output out of a turbocharged engine, you don't need to have that big size of engine. So you can probably have a smaller engine with the right turbocharger attached, give you the same power output as a bigger size naturally aspirated engine. So again, that's one of the benefits of turbocharging on an IC engine. Fuel economy. So we were talking about, emissions. We were talking about um, we were talking about emissions legislations, talking about more power output. Fuel economy is also improved because obviously you have a better combustion process, and which means that with turbochargers they can increase the thermal efficiency up to around 45% in certain heavy duty automotive engines, which obviously helps with the fuel economy. Maintains the engine performance at high altitude, which means, so this is called as altitude compensation. And that is primarily because if you imagine using a naturally aspirated engine at high gradients, what happens is the atmospheric pressure drops at such heights. And because atmospheric pressure is dropped, and naturally aspirated engine purely depends upon atmospheric pressure because it's a naturally breathing engine. Because there is less air and obviously air injecting fuel, what happens is basically coming out. And with turbocharged engine, what happens is that it helps you to sort of give you that air by sort of using up the work of the turbocharger, and then by doing that you'll basically have the same level of power output that you get at the sea level, even at altitude. So helps you for that altitude compensation. um, I sort of briefly touched about on this topic. So turbocharger can support other functions. When I say that, it's about engine braking and thermal management. So engine braking is again when you need to use engine as a brake. You have your vehicle brakes to stop the vehicle, but some might already know that you can also use your engine as a brake by increasing the back pressure. When I say the back pressure, the pressure which is sort of coming from the exhaust manifold into the turbocharger, if that is sort of blocked somehow, that means that your turbocharger can no longer receive the exhaust gases from the engine, which means those gases will not have anywhere else to go, which means it will stop the working, it slowly stop the working of the engine itself, which means it's also acting as a brake. So that's a very important feature as well, engine braking. And there are there is the other one, which is the thermal management, where I talked about after treatment system, where all the exhaust gases are will be sort of reduced before it's let out into the environment. And turbocharger plays a major role because it can give you the high temperatures that those systems will need in order to break those particulate matters. Before they are let out into the environment. So it also helps you in the thermal management area. So these are probably some of the examples of why turbochargers, why turbocharge an IC engine, what are the pretty much the uses of turbochargers in IC engines. So on this slide, what I've shown is quite a few examples of turbochargers. So let's go through one of them one by one. So the first one is fixed geometry turbocharger, and by using a fixed geometry turbocharger, what I mean is that the turbocharger basically is fixed. Like there are the airs coming through the turbine inlet side. This is where the it's connected to the IC engine. It sort of goes out to the turbine outlet. It spins this wheel, and because this wheel is spun, it also spins the compressor wheel, where air is taken from this side. It compresses, and then it sort of goes out into the outlet side. You can sort of have a very small output to a very large output just by moving this nozzle. So that is why it's called as a variable geometry turbocharger. And other than that, obviously we've got other complicated systems as well, depending on what customer requirements are. How much the power output do they need, and what are the requirements and how we need to meet it. So some of them engine information. What we do is we basically look at we have a portfolio, and we basically create create sort of maps for those portfolios. So we have the maps for each of the turbocharger that we have. So we'll sort of have to do that. Then we go back to the customer and say, this is what we think would help for your engine to achieve this level of performance target, this level of emission targets. Obviously, there'll be discussions about what we can do and what we can't do, and there's always some level of compromises that will be required. But that is probably how we sort of initiate those discussions. So we have to go through a process, and this process is called as engine matching. And after this process is done, then further discussions will happen. So what I'm now going to show, the next 3 slides, is basically just give me 1 second. Is basically some examples of what we you're creating like a nozzle effect at the end of your hose. What that does is that although the flow which is coming through the hose is the same, the pressure of the flow which goes out is higher because you're reducing the flow. That's what the smaller housing means. So the flow will be the same, but the pressure will be the higher. And that's like a danger zone because you can't go above a certain speed range. So that's what the problem is with at the limitation, I'd say, with a standard housing, because you can change it to a smaller housing, but then it goes too far. So you need to control it around this area. And that is where a wastegate comes into picture, because if you are having a smaller sized housing, it sort of has higher pressure. And with the wastegated housing, we probably have that because you can open the flap when you don't need it, and that's what probably happening here. So in a wastegated housing, or let's say the blue color curve, you're opening the valve and closing the valve when you need it, and you don't need to go into the danger zone. So we can stick within the limits that we need for the turbocharger. And similarly with the variable geometry, it's much more better because because it keeps moving back and forth, and you can alter it at any configuration. It's the highest performer of all the different configurations because it can vary back and forth. And you can change it to behave like a small turbocharger. You can change it to behave like a big turbocharger because it sort of keeps that nozzle moving back and forth, which sort of can create a smaller expansion or a bigger expansion depending on what the requirement is. And that's why you have the cyan blue color here, which sort of shows it's above all the other different configurations that I showed you. So this is probably touching into some of the real-time applications. So it's not I'm not sort of gone into any, but at least it gives you a flavor of what the different turbochargers are, how are they sort of applied. The next slide is, pretty much just wanted to sort of share my experience in terms of my career journey till date. And obviously I hope that it will be useful for students who are currently in their 3rd year, 4th year, and thinking about their next steps. So I did my bachelor's in mechanical engineering, and at that time I had my sort of goals before joining bachelor's of mechanical engineering. I had my interest towards either towards mechanical or aeronautical engineering. But then I decided that firstly I wanted to do my mechanical engineering so that I get a strong foundation on the different elements of mechanical engineering, and then try and do my think about what masters that should be done. And when I joined my mechanical engineering, I did quite a few various projects on IC engines, which is what made me hook up more towards IC engines and automotive engines, which led me on to do my master's in automotive engineering at Cranfield. And when I did my master's, I worked on a Nissan engine as my research project. So I did IC engine valve train friction as my research project, which was more closer to what I was passionate about doing. And then after doing my masters, it was it was a hard task of finding, a job. And at that time, UK was just coming out of recession, so it was a difficult task to find a role which which obviously met your criteria of your education. And I was fortunate to get a role with Cummins as a graduate engineer. And thereon, I started doing different roles within Cummins. And when I started doing the product engineering, I also sort of joined the IMECI program. In IMECI, there was a mentorship program which you could join to gather more expertise and experience from people who are already in the industry for so many number of years. And and then I started doing systems engineer, where before systems engineer, in product engineering, the role I was doing was looking at small components, or smaller aspects of the turbocharger, and how to sort of validate them, how to design them. Those were the sort of things which I was looking at. When I moved to systems engineer, the role that I did was in terms of how does this turbocharger work on the customer engine. So what are the tests that we need to do to make sure that this turbocharger does not fail on the field, or what are the design changes that you need if it fails. So those are the things which I looked at as a system engineer. And alongside that, I also did my Six Sigma certification, and also I did my program management certification within Cummins. What that helped me to do which is what I'm currently doing, which is a technical project leader role, which means that I look at the projects as a whole. So which means that I basically take care of when the customer comes into Cummins and they say this is what we want. That's from where I start my role in terms of understanding customer requirements, designing what they need, doing a lot of testing. We are meeting their requirements, and if you're not meeting, then what we can do to meet the requirements, and then finally, sending it into production. Though this is a long journey, the projects that sort of go through is like, it can typically take anywhere from a year, or up to 4 or 5 years, depending on the complexity of the project. So it's a fascinating role that I'm currently working on. And the next slide, I'll sort of show you where the different customers sort of worked with so far. I've basically shown quite a few pictures here. Again, hopefully this will inspire some of you to choose your paths moving forward. And when I was in SJC in Chennai, this was a project that we did as college students. We wanted to look at a dual fuel vehicle. This is a TVS Champ, if you can recognize it. And we basically took that and we integrated that with a battery and with a hybrid system. And this was 12 years before, when hybrid was quite a bit of a new area at that time. So, this is with our director, Dr. Babu Manohar at that time, and our assistant HOD, Vadi sir, which we basically, so that was helped us to understand a bit more into how hybrid can be integrated into SI, gasoline engines. And again, as I mentioned, also my next journey was to Cranfield. The transition from India to UK was quite difficult. It was not easy because the curriculum and the methodology of how the education is treated in UK, it's quite different, and it's more about research and using the library to understand your knowledge, and it's more application oriented rather than theoretical. So that transition was difficult, but again, being adaptable to different situations and conditions helped to capture it quite early and then get on with the game. And I also mentioned about IMechE. That was another important milestone in my career because IMechE helped us to understand how important engineering is and how structured it could be. And once I did the mentorship program, then they awarded with a chartered engineering certificate. So that's the highest honor you can get as an engineer working in the industry. The next picture is about yes, it's a few customers that I worked so far. It's not a lot, but I feel that every customer that I work and every global location that I work, it's everything adds a new experience and a new perspective to things, and you learn from experience as well. I think that's the key thing over here. You work with a lot of people and then you learn a lot of things and use them in your career. In terms of working with schools, I also sort of take as a science, technology, engineering, and mathematics. So that's called a STEM. I go to schools and then work with young children, trying to teach them about technology and engineering, and we do quite fun activities which sort of has engineering as engineering as the core element. So that helps them to understand engineering can also be fun and it's not a boring subject. Then I was also a school governor, so this again helped me to work with people within the school itself and sort of brought new perspectives of how a school is run and what are required for the running of the school. So again, this is a quick snapshot of my key experiences in this industry. All right, so we are quite near. So I just want to wrap up basically by obviously sharing some knowledge in terms of what the market is currently expecting. So everybody sort of is aware about what's happening in the outdoor world. So the restrictions and the regulations that we have are not decreasing. They are increasing day by day. So Europe is basically looking at Euro 7 norms. India is looking at BS6. I think BS6 should have already come now by now. And China is looking at NS7 and stage 4 fuel norms. So there's quite a few stringent emission regulations which have already come and which will sort of get tightened more and more. So market is basically looking at more efficient products which can handle this economy. Fuel, give you better fuel economy and have better emission regulations. And in terms of diversification of energy resources, the key for this is that sort of everybody will be aware that there are quite a few different companies, electric companies or hybrid companies, or diversification of fuels will be a key key player moving forward. And I think that is probably where it may have probably helped to address some of the prior concern, but it's going to be a challenge. It's not going to be a easy playing field. So there's going to be quite a few challenges in terms of how they handle the aerodynamic aspect. How do they keep the same weight of or how do they reduce the weight of the engine or the chassis or the vehicle? How do they maintain aerodynamics by integrating X, Y, Z? So there's going to be quite a few challenges. How are they going to charge the batteries if this is going to be an electric? So there's going to be quite a few. That's something to look forward for. In terms of cost, where the more pressure from the OEMs or the original engine manufacturers, there's very little margin for error in that case. So there's the stringent requirements, the more and more requirements, but there always one requirement which just changes the cost. So they still need all this all the improvements or the enhancements, but it comes down to a balance of how costly it is as well. And I think moving forward, the OEMs will sort of will sort of start thinking about what does the customer actually need, and is actually nice to have. So there is quite a bit of difference between a need and a nice to have. And probably they'll be trying to integrate different models into one platform to sort of improvise on the cost. So there's quite a lot of work which will be required in that area. More work is probably required to sort of have this thought, and then help them, which will probably help them to increase their profits amidst all the tightening regulations, which is probably the right thing to do. And the last one is engine digital technology. So the key reason I put it is connectivity is getting day by day important. So everybody sits into a car and everybody wants their phone to be connected to the car straight away, so you can enjoy your music or your phone calls. So we need a smartphone, we need a smart bulb, we need a smart car, we need everything smart now. So everything is becoming smarter now. So and then digital technology, I think this is where it plays a key role. So the OEMs or the engine manufacturers or the automotive company about how to get this connectivity. So in Cummins, what we have is the engines will be sort of working in some part of the world, but we've got complex technologies which can enable us to move faster and quicker. I think this slide is pretty much to sort of talk about the same area, where complex technologies which need to be innovated moving forward, which sort of helps with all the regulations coming up. So that's pretty much it what I had from me. I've got a bit of time, I think, for the questions. Sorry, I didn't have a lot of time, but feel free to sort of we'll probably have 4 or 5 minutes for question now. Is it correct? Whatever.
Yes, sir. Am I audible, sir?
Yes. Go for it, Stuart.
Here we have a question from Ashwin. The question goes as follows. Sir, we know that the combustion requires oxygen. In the case of turbochargers...
Sorry, you're breaking up, Sooraj. Hello? Sooraj, can you hear me? I can't hear you, unfortunately.
It is used in exhaust pipe and
I can't hear you, unfortunately. Your voice is breaking up, Sooraj. Can
exhaust
somebody...
carbon monoxide is the end product.
Hello, Sooraj.
Am I audible?
No, your voice is breaking. Sir, I will let you know the question.
Hello.
Yes, sir. Is it audible?
Hello, sir. Am I?
No, your voice is wavering.
Hello, sir.
Yes, Ahmad.
Can I just have a question? It's not regarding turbocharged, but what's your opinion regarding EV vehicles over ICE vehicles?
What is, sorry, your voice is breaking up. So what is I didn't hear your last. Maybe somebody else could you help Sooraj in the questions?
Yes, sir.
Is it audible right now, sir? Am I clear?
Yes, Sooraj. Your voice is clear.
We have a question from Ashwin. The question goes as follows. Sir, we know that combustion requires oxygen. In the case of turbocharger, it is used in exhaust pipe, and in the exhaust, carbon monoxide is the end product. If we pump the same carbon monoxide back into the intake valve, will that have an effect in accumulation of carbon in the intake valve?
Okay. We burn the carbon monoxide. So I think carbon monoxide. Carbon monoxide is a harmful stuff, right? So it's burnt, and and most of the fuel is basically burnt to carbon dioxide. The proportion of carbon monoxide is quite small. So what we have is, the catalytic. I talked about, the after treatment system, the catalytic converter, all the complicated after treatment systems that we have, which sort of include, ER, SCR, DPF, DOF, all the sort of, after treatments help. That's what they do. They break out this harmful carbon monoxide into carbon dioxide. So what we get as a byproduct is carbon dioxide, which is what we sort of let out into the environment. Does that answer your question?
Yes, sir. I hope it answers. And then we have question from Narayan and Murthy. Can you please explain about the maintenance needs in?
Yeah, sure. So in terms of, obviously, in terms of maintenance, obviously we'll have, as a turbocharger company, we ask the customer to obviously have good oil maintenance. We'll basically say this is probably when the oil needs to be changed and all that sort of stuff. So that is part of our regular maintenance that we do for the turbochargers. What we also say is we talk about filters in terms of air filters and stuff like that, the quality of the air going into the turbocharger, so air filters and all that. So in terms of maintenance, obviously we have certain requirements which we basically mention to our customers. Some of them the filter change at certain intervals of time.
Yes, sir. And then we have a question from Rishabh. The question goes as follows. In gas turbines, ramming action of inlet air given in good combustion. Is ramming action significant in automotive systems?
I'm not sure I understand the question clearly. What does ramming action mean?
If possible, Rishabh, can you unmute and
Hello, sir. Am I audible? Hello, am I audible, sir?
Yes, you are, sir. Yeah, go on.
Sir, ramming action involves increasing the pressure of the inlet air by decreasing the area, decreasing its area.
Okay.
So, is it significant in automotive systems? Like we can decrease the area of cross section of entering of the inlet air. So velocity increases and thereby more pressure difference. The more the flow rate of the inlet air increases. So can we do that?
Maybe, well, I'm not sure I could possibly answer the question, but what my thinking is, maybe at high speeds, this is probably where the because of the ramming action, the you increase the inertia of the. Okay.
Thank you, sir. And here's one question myself. And like nowadays, the number of electric vehicles are increasing in every countries. In electric vehicles, there's no case of that pollution. That case is the market of so turbochargers going to decrease soon. Not immediately after probably after few years.
Okay. Yeah, I understand the question. So we are taking. We basically have, as I said, we basically have turbochargers to do quite a few functions, and with obviously with electrical engines, we are still trying to understand how we could help the electric vehicles in regards to other functionalities. I talked about engine braking. I talked about more power output, talked about, thermal management, etc. So we talked about quite a few varieties of uses. So I think we are still exploring that area. So I think there's more to watch out and watch the space.
And we have a question from Khairul Azhar. As Cummins engineer, what do you Cummins engines is different and special if compared from the other engine manufacturers like Caterpillar, BMW, Suzzler, etc.?
Okay, well, I don't think I'll be in a position to sort of compare against other OEM manufacturers, but I think from a Cummins engine's perspective, what we deliver is a clean, efficient, dependent, and a durable product. And from a Cummins, we are doing engines for pickup trucks from small pickup trucks to 18 wheel trucks, basically. So anything from a small berry picker, that's what they call in the US. They call a berry picker, to a 360-ton mining haul truck. So we will provide engines for quite a variety of applications. There's Cummins engine used in the water, in rail applications, in bus applications. So there's quite a few applications and a wide range that we supply these engines for. And where we set the bar is in terms of performance and reliability. So we actually have the highest, the best products out in the field, which are more reliable. And we've been doing this for more than 100 years. So I think probably that should sort of answer some of the question. And we are also looking forward in terms of the future where we can deliver, a zero emission natural gas engines, electric engines, hybrid, alternative fuel powertrain technologies, etc. So not only we are, global leaders in terms of, engines, we're also looking forward to what we can deliver moving forward in the future. So I hope that sort of answers, some of your questions.
We have one question from lastly from Ashwin. Sir, we know that naturally aspirated engines are conventionally used in most of the automobiles. In automobiles with turbocharged engines, why are they priced at a higher price compared to naturally aspirated engine, as they involve only the installation of a turbocharger compared to the naturally aspirated engines?
Okay. So again, these are naturally conventional automobiles with turbocharged engines. Why are they priced? Well, I'm not. I can't give you a clear-cut answer, but I think if you look about it, like if you have a naturally aspirated, whether you're able to compare the same engine of naturally aspirated just with an addition of a turbocharger, or they have other additions to the, I'm not being, I won't be able to compare those differences. But more the elements, more the complexity, more the the cost. Obviously, that's how I'd like you to look at it. So if you have less parts, obviously you have less complexity. If you have more components and more, so you obviously are looking at different issues which may come in the field. So all that gets factored, etc. So into the model. So I don't think I've answered you 100% on that question, but I think that the idea behind it is that you think about it as components complexity wise, which looking at cost.
With now the last question from Rishabh, we'll wrap up with the question and answer session. And what is the role of CFD simulation in the design process? Wrap up the session, sir. Thank you so much for that, answering all the questions patiently. We'll come to Mr.M.Vadivel, sir. Sir.
Yes. Thank you, participants. First of all, I thank. One second. I thank our speaker, Mr. Avraham sir, for accepting our invite in a very short while. Thank you for a wonderful session, sir. From the basic IC engine to supercharged engine, turbocharged engines, then sharing your firm products, and for sharing your career experience. Thank you, sir. Thank you, sir, for a wonderful session, for sharing your knowledge. On behalf of MEENAKSHI Engineering College, Mechanical Department, I thank you, sir. Thank you for the participants for your questions. I hope all the questions has been answered by the speaker. Thank you, sir. Participants can fill up their feedback form. I have posted the link in the chat box.